We want to extend our ability to integrate to exponential and logarithmic functions. Remember, we know how to take derivatives involving exponential and log functions. We want to extend that to being able to integrate those. But first, I want to remind you that when we first learned about integration by substitution, beyond the guess and check method that we started with, we talked about two other methods of integration, and I asked you to look at the one that you are most comfortable with and then to stick with that method. Remember, one method was called, at least we called it, integration by matching. If that's your preferred integration method, you should watch the first 26 minutes of this video. And you can just skip the rest of it unless you just want to go back and look at the other method again. It's just the same problem solved again by the other method. Then, if you decided that the method we called integration by direct substitution is your preferred method, then you probably want to skip straight to the 26-minute mark and watch from there all the way to the end. And that will be showing the same problems solved by direct substitution. So let's start off with the integration by matching portion. And again, if you prefer the direct substitution method, you probably want to skip ahead to that. The main thing to remember on these is that since the derivative rule for exponentials is so simple, it's really not going to be surprising to see that the integration rule is also simple for exponentials. In fact, I'll just show you. The exponential rule for integration says that the integral of e to the u du is simply e to the u plus c, the constant of integration. Again, simple as it could be, the integral of e to the u du is e to the u plus your constant of integration c. And let's just jump right in and remembering that we're doing the matching method here. Here's our first example. Suppose we want to integrate e to the power of 7x plus 5 using substitution by matching. The first thing we're going to do is set u equal to 7x plus 5. Why? Because the exponent in the exponential rule for integration says that's what u is. U is the exponent. So we set it equal to 7x plus 5. And then we compute the differential. The derivative of 7x is 7, so we get du is 7 dx. Now we set up our matching. I just spread it out to give us some more space because what we want is for the differential du to be at the end. We already know that u is 7x plus 5. The differential du has to be at the end, and if you notice, we already have the dx there, but we don't have 7 dx. But as we know, we can fix that as long as we're off by at most a constant. We can fix that by putting a 7 inside to the left of dx as long as we compensate by multiplying by its reciprocal, which will be 1/7 on the outside. This is what our matching method teaches us to do. So now what? Well, do the formal substitution. The 7x plus 5 becomes the u in the formula, and the 7 dx becomes du. So now that we've matched them, we can substitute and get rid of the original x's. Notice that once you do the substitution, you no longer have any x's in the problem, but you do have that 1/7 out front. Don't forget that. The 1/7 is just going to sit there for the time being, but we have to integrate e to the u. Well, what is that? Well, luckily, we have the answer right there in the rule. The integral of e to the u du is e to the u. And in our case, with the 1/7 out front, and please don't forget the constant of integration, so it's plus c. That u has to be removed before you finish because we put that u in there ourselves. The u was not in the original problem. So the very last step is to take the u back out and put what it's equal to, in this case 7x plus 5. And that gives us our final result. Simple. Let's do another. Suppose we want to do the integral of 7x e to the power of 9x squared. Process is exactly the same. Since the exponent in the formula at the top is the u, that tells us that we need to set u equal to 9x squared. Now compute the differential. Du is the derivative of 9x squared, which is 18x, dx. Then you look back and you notice that you've got some components of the differential, but they're not in the right place because you need the x to be next to the dx here. So I'm going to move the x to just to the left of dx. I also notice I have a constant factor of a 7. You can always move a constant factor outside of the integral sign if it makes your life easier. So I'm going to choose to do that here. So the 7, because it's just a numerical factor, can be put out front. I'm taking the x and moving it to just to the left of the dx because I know I need it at the bottom, and I need more than that. In fact, let's make a little bit of room. I'm going to spread things out a little bit, and the reason I'm doing that is because I need to put that 18 in there. I have the x dx, but I don't have the 18. So if I put the 18 to the left of the x, I can do that as long as I compensate by putting a 1/18 on the outside. Now, of course, 7 times 1/18 is going to turn out in the end to be 7/18. I'm not going to worry about the constant right now. But remember that the 9x squared is the u, and the rest of the integrand, including the dx, all of that forms du. So I can make the substitution, and again, I said 7 times 1/18 is going to be 7/18. But the critical part is noticing now that I've gotten rid of all the x's. The e to the 9x squared became e to the u, and the 18x dx became du. And now I can look back at the top and notice that the integral of e to the u, according to our formula at the top, is just e to the u. And in this case, the 7/18 is out front, so it stays there. We're done with the integration, but we still have a u in our answer, and the original problem did not have a u, so we have to take it out. So we put the 9x squared back in place of u to get our final solution. Again, if you could do earlier problems using matching, then there should be no issue doing it here. You're just matching a different formula. How about this one? The integral of the quantity 2x plus 6 multiplied by e to the power of x squared plus 6x. Again, the problem sort of tells you what to do to get started. U is going to be the exponent on the e. So that tells me immediately I need u to be x squared plus 6x. The differential is the derivative of u times dx. So the derivative of x squared is 2x and the derivative of 6x is 6. You need those parentheses though, so the differential du is the quantity 2x plus 6, you need those parentheses, times dx. And that's exactly what we see up here. So we really don't have to adjust it at all. When you get an exact match, notice the 2x plus 6 is not just to the left of the dx, but it's just very simple to move it over there. So I can move that 2x plus 6 so it's just to the left of dx, and now everything matches. That 2x plus 6 quantity dx is the differential du, and of course, as we said earlier, the x squared plus 6x in the exponent is the u. Now I don't have to make any other adjustments. I can do the substitution and get e to the u du. And the integral of e to the u du from our formula above is just e to the u plus c. And never forget to substitute back when you're done with the integration. We put the u in there. We have to take it back out at the end. U was x squared plus 6x, so we take it back out and get our final solution. This is all very simple if you understood the substitution by matching method before you came into this section. How about another? Suppose we have the integral of the quantity x plus 3 times e to the power of x squared plus 6x. This is very similar to the one we just worked, but this time the integrand has got a factor that's going to make it not match the differential exactly, so we'll have to adjust it. You'll see as we go through. But as before, the choice of u is simple. It's going to be the exponent on e, which in this case is the same as the previous problem, is x squared plus 6x. The differential is exactly the same as it was before. That part of the problem didn't change. But we don't have a 2x plus 6 in the integrand. However, we do have an x plus 3, And if you notice, there's a common factor of 2 in the differential. So if you factor it out, you'll see that you get 2 times the quantity x plus 3 times dx. And I did that because I could see that I needed to. I was trying to get an x plus 3 into the problem because I saw an x plus 3 in the integrand. So in order to get that x plus 3 into the problem, I factored a 2 out. So it's just a minor point in terms of the algebra, but it's an important point in terms of getting through this substitution. You have to realize that sometimes you're going to have to factor out something in order to proceed with your matching process. But anyway, now that I've factored out the 2, I can see that that's what I'm missing from the integrand. Let's rearrange things. I know that I need this x plus 3 to be next to the dx. I'll move it over. So if you just take that x plus 3 and slide it over so that it's next to the dx, it appears over here instead. My differential is closer to being right. The only thing I'm missing now is a 2. Notice that the differential that I need has a 2. So that means I have to put a 2 in there, which I can do as long as I multiply by 1/2 on the outside. Look at the big picture. You had to notice that you needed to factor a 2 out of the differential. But other than that, it's just a straightforward process of rearranging if necessary, multiplying by a numerical factor if necessary, while compensating on the outside. But the basic process is the same. At this point, I have my match. I can see now that the 2 times the quantity x plus 3 dx is sitting right there, so I can call that du. And of course, e to the x squared plus 6x is going to become e to the u. Carry out the substitution. Do not forget that the 1/2 just carries along for the time being. And so I'm going to have to get an answer of 1/2 times that integral. Luckily, I know what that integral is because the formula tells me that the integral of e to the u du is just e to the u plus c. So I put that in there, not forgetting that the 1/2 just carries along. And as always, the last step is to take the u back out and put in this case, x squared plus 6x. And there you go. Very straightforward, very simple. If you understand the substitution by matching method, applying it to our new exponential rule for integration is actually very easy. Now let's switch our attention to logarithms. In the same way that we suspected that the integration rule for exponentials was going to be simple because the derivative rule for exponentials was simple, we also suspect the same will be true for logarithms, and that is the case, although there is one little minor issue that I do want to address. Remember that the derivative of the natural log of x is 1 over x. So on first thought at least, you'd think, well, shouldn't the integral of 1 over x dx be the natural log of x plus a constant of integration? And that's almost right. And the only thing I want to say about that is you can't take the logarithm of a negative number or 0. So the domain of the natural log function is 0 to infinity, an open interval. In other words, the log can only take a positive argument. So in order to account for that, and at the same time I'm going to change from x's to u's, that log rule for integration has to say that the integral of 1 over u du is not just the natural log of u plus a constant, it's the natural log of the absolute value of u plus the constant. Given that, yes, the log rule for integration is very simple. The integral of 1 over u du is the natural log of the absolute value of u plus c. And we'll continue the matching examples for the logarithms as well. I do want to mention one other thing that's maybe a minor point, but it does need to be mentioned. Going all the way back to the general power rule for integration, we learned that to integrate u to the n, you increase the exponent by 1 and then multiply by 1 over that increased exponent on the outside. But that formula doesn't work if n is equal to -1, because if you try to plug a minus 1 in for n plus 1 in your formula, you're dividing by 0. So that formula never worked for n equal minus 1. But think about it a minute. So what is u to the minus 1? Well, u to the minus 1 is 1 over u. That's exactly what the log rule does. So I guess what I'm trying to say is this case for the logarithm rule is actually filling in the gap that the general power rule left, because we could never let n be minus 1. If n is equal minus 1, then you have to go to the log rule. So just keep in mind that the log rule fills in a gap that we've had all along with the general power rule. Having said that, that doesn't change the fact that using the log rule for integration is still very simple. Now let's just do some problems. What if I have the integral of 1 over the quantity 7x plus 1? Well, if you look back and look at the formula, you can see your substitution sitting right in front of you. The u should be the denominator, 7x plus 1. And if you compute the differential, you get 7 dx. du is 7 dx. Now, I'm going to scoot dx over to the right a little bit to leave some room, because you see where I'm going. I need a 7 in front of that dx, because the differential is du equals 7 dx. But I can handle that. I can always insert a numerical factor as long as I multiply on the outside by its reciprocal. So if I put a 7 on the inside, I have to multiply by 1/7 on the outside. Now it's nice. The denominator of that fraction becomes u, and everything to the right of the fraction becomes du, and when I substitute, I get 1/7 times the integral of 1 over u du. And now I'm off to the races. I know that the integral of 1 over u du by the log rule for integration is the natural log of the absolute value of u plus c. Don't forget the 1/7. And then the last step, as always, is to take the u out and put back in what u was equal to, which in this case is 7x plus 1. And there you go. Very straightforward. How about this one? Initially, this problem looks difficult, but if you think about it a minute, our log rule for integration gives us an indication that we should let the denominator be u. Also, you'll see that the formula has a 1 over u in it, so it might be nice to take the integral and make it look like that. And we can easily do that. All we have to do is take the numerator and push it out of the numerator and put it beside to the left of the dx. And so we're taking it from the numerator and moving it to the left of the dx. Now you can see the 1 up top, and the integral is taking shape now. So I think I see what's happening, and I can confirm that by doing the differential. If I do, in fact, let u be the denominator, I get u equal x cubed plus 3x squared plus 12x. Then the differential is 3x squared plus 6x plus 12 quantity times dx, and you need the parentheses around that 3x squared plus 6x plus 12. It looks like I don't have a match, but that doesn't mean that things are hopeless, because we've learned in the past that if you see a common factor in the differential, you can factor that out, and that might help. So there's a common factor of 3 on the right-hand side of that differential, and if I factor it out, now I see where things are headed. I see the x squared plus 2x plus 4 in the differential, but I also see it in the integral. But I'm missing a 3. So looking back at the formula and looking back at where I'm standing, I can see my differential du forming. I'm just missing that 3. But that's okay. Everything but the 3 is there. I can put a 3 in as long as I multiply by 1/3 on the outside. And now you can see that my differential is complete. 1 over u is the way I want it to be. And now I can take all the x's out. Don't forget the 1/3 out front. And I get 1/3 the integral of 1 over u. And everything to the right of the fraction is part of the differential du. So what looked like a messy problem is actually not so bad. Now that I've got the integral 1 over u du, I simply apply my log rule for integration formula and write that as the natural log of the absolute value of u plus c, not forgetting the 1/3 out front. And final step, as always, is take the u out and put in what u was equal to, which in this case is x cubed plus 3x squared plus 12x. And there's your solution. What looks so messy turned out not so bad. Step by step by step. How about this one? Well, it's got exponentials in it, so your first thought is, well, that should be back in the problems where we were doing exponentials. But that's not the case, because if you think about it, this e to the x can be taken out of the numerator and pushed out front just like the previous problem. So you're sort of seeing a 1 over u type of problem here, and that's what you should be seeing. So if I try that and let u be the denominator, which would be 4 plus e to the x, the differential of 4 is 0, and e to the x is e to the x. The derivative of e to the x is e to the x. So the differential is du equals e to the x dx. Now I can sort of see what's going on. I'm going to take that e to the x and push it out of the numerator and put it to the left of the dx. That leaves a 1 in the numerator. So now I'm starting to see the behavior I like. I get that 1 in the numerator. Everything to the right of the fraction is going to be the differential. It's an exact match. So this is looking really good very quickly. The e to the x dx is an exact match for du. And the denominator, the 4 plus e to the x, is u. And I can get rid of everything that has an x in it. And it comes down to 1 over u du, that integral. And I know that that is the natural log of the absolute value of u plus c. And of course, the last step, as always, is to take the u back out. And there's the answer. So the challenge in this problem is to recognize that even though the integral had an e to the x in it, it was actually a problem that was going to turn into a 1 over u type problem. Practice makes perfect. Doing enough of these, you'll start to see when that happens, and you'll be ready for it when you see a problem like that. I want to make one more point, and that is, I haven't mentioned the guess and check method. I sort of mentioned there were two methods after we passed guess and check. I'm not going to shortchange guess and check though, because anytime guess and check can be done and you're confident in it, you're welcome to use it. We've talked about in the past using it mostly for the simplest cases, and I would say the same thing here. You're free to use guess and check anywhere you feel confident doing it. I'm going to do one example, very simple, and show you where guess and check could be used. I'm not advocating for it or against it. I'm just saying that if you're good at guess and check and feel confident, any problems you feel like that about, you can do by guess and check. So suppose we want to use guess and check on e to the 2x dx. I know that the integral of e to the u is e to the u, so maybe my guess is that the answer is e to the 2x. Guess and check says to check your guess by taking the derivative and see if it matches the integrand. The derivative of your guess has to match the integrand. But the derivative of e to the 2x is e to the 2x times 2, because the derivative of an exponential is the exponential times the derivative of the exponent. And of course you can write that as 2e to the 2x. And you can see it doesn't exactly match. You get the e to the 2x part, but you don't get the 2. In fact, your answer has a derivative twice as large as we want. Remember, guess and check says if you're off by a numeric factor, that's okay. You can adjust the guess, and since my answer came out twice as large as I was looking for, maybe I'll go back and adjust my guess to be 1/2 e to the 2x. And what do? You check your adjusted guess by taking its derivative and see if it matches the original integrand. Well, the derivative of 1/2 e to the 2x, the 1/2 just sits there, and the derivative of e to the 2x is e to the 2x times 2. But this time, the 2 and the 1/2 multiply each other away, and you get e to the 2x, which is in fact an exact match for the integrand. Since it was an exact match, our adjusted guess, which was this 1/2 e to the 2x, is the answer. So the integral of e to the 2x dx is 1/2 e to the 2x plus c. That's how you do it by guess and check. I'm not advocating that you do it that way. I'm just saying if you feel comfortable doing it, it is an option. Otherwise, you just go back to your substitution by matching method. Because the derivative rule for exponentials is so simple, it's really not surprising that the integral rule for exponentials is also simple. And I'm just going to throw it out there. The integral of e to the u du is e to the u plus a constant of integration c. Now here I'm going to use the direct substitution method for the problems that follow. But if you prefer the integration by matching, you can go back to the beginning and watch the first 26 minutes. But here I'm going to use the direct substitution method. And let's just jump right in. Suppose I give you the problem, the integral of e to the 7x plus 5, and ask you to find the integral. First thing you want to do is notice that the u is the exponent on the e. So that would be the 7x plus 5. So the initial step is to let u equal to 7x plus 5. Then calculate the differential. Du would be 7 dx. Next, you want to solve for dx. If you divide both sides by 7, or saying it the same way, multiply both sides by 1/7, you get dx is 1/7 du, or you could say dx is du over 7. In either case, you know the u is the exponent on the e. That would be the 7x plus 5. And that dx is what you just solved for down below in the box. Dx is 1/7 du. If you substitute those two things in, then all your x's vanish. The e to the 7x plus 5 becomes e to the u, and the dx becomes 1/7 du. Now we all know that a constant factor inside an integrand can be brought out if it's needed to be, and I think that's what I'd like to do here. At this point, I see that e to the u du in the integrand by formula is e to the u plus c, not forgetting to copy the 1/7 out front down. You end up substituting back in at the end, get rid of the u, put the 7x plus 5 back in because we put the u in to start with. We have to get rid of it when we're done. So the integral of e to the 7x plus 5 is 1/7 e to the 7x plus 5 plus a constant of integration. Let's do another one. Suppose we have 7x times e to the 9x squared and we want to integrate that. Same process. We know that the exponent of the e will be the u. So we actually write that down. Then we compute the differential. The differential will be 9 times 2 is 18x dx. And then we solve for dx. We end up with 1 over 18x du, or you could say that is du over 18x, either way. The point being, we now know that we can get rid of the 9x squared and call it u, and we can get rid of the dx and call it 1 over 18x times du. Doing that, we noticed that the 1/18 x, I'm just going to slide it over next to the 7x because that's where all the action is. I notice that 7 x is like 7x over 1, and when you multiply fractions, you do top times top, bottom times bottom, so that turns into 7x over 18x multiplied by e to the u du. The x's divide out, and you end up with the integral of 7/18 e to the u, and you can, as we've done earlier, bring out a factor that's just a number if you want to, and I do, and that gives me 7/18 times the integral of e to the u du, which I know from above is equal to e to the u plus c. So I end up with 7/18 times e to the u plus c, and the last step, as always, is to take the u out and put back in what it was equal to in terms of x, which is 9x squared. Fairly simple, straightforward process, but you need to practice it. How about this one? We've got the integral of the quantity 2x plus 6 multiplied by e to the power of x squared plus 6x. Same idea. U is equal to the exponent, so that would be the x squared plus 6x. Set that equal to u. Compute the differential. That's 2x plus 6 quantity dx. You need the parentheses around the 2x plus 6. There is a 2x plus 6 dx in the integrand, so we matched exactly already, just as an aside. And then we decide we need to solve for dx as usual when we're doing the direct substitution method. So dx would be 1 over the quantity 2x plus 6 du, which you could also write as du over 2x plus 6 if you like. In any case, the x squared plus 6x comes out as u, and the dx comes out as 1 over the quantity 2x plus 6 du, giving you this expression. The 2x minus 6's divide out, leaving you just with e to the u times 1, which is just e to the u, inside the integrand. And as we've noticed before, that integral by the exponential rule for integration is e to the u plus c. The last step, as always, is to put the x values back in. U is x squared plus 6x. When we put that back in place of x, we get e to the x squared plus 6x plus a constant of integration. Again, straightforward, step by step, takes practice. All right, this one, same idea. The u would be x squared plus 6x, the exponent. So we write that down. Find du, that would be 2x plus 6 quantity times dx. You need those parentheses. This time there's not an exact match though. Whenever there's not an exact match, all hope is not lost. I do notice that there's a common factor of a 2 that I can factor out, and sometimes that will lead you into the right path. So if I factor out that 2, I notice, aha, I see that x plus 3 now. It's 2 times the quantity x plus 3 dx. So I'm close to a match, and I'm only off by a factor of 2. Continuing, I know I need to solve for dx. So dx is 1 over the quantity 2 times x plus 3 du, or you could write it du over 2 times the quantity x plus 3. Either way. But when you go back and substitute, the x squared plus 6x comes out as u. The dx comes out and is replaced by 1 over the quantity 2 times x plus 3 times du. And now you can see that the x plus 3's divide out, leaving you with the 1/2 and the e to the u du. We know that a constant factor can be brought out of the integration sign if we like. I'm doing that. And then it matches. E to the u du is e to the u plus c. Don't forget the 1/2. And the final step, as always, is replacing the u with what it's equal to, in this case x squared plus 6x, and we get the final answer 1/2 times e to the power of x squared plus 6x plus a constant of integration. It's just practice, practice, practice. Now let's switch to logarithms. Again, since the derivative rule for logs was fairly simple, we should expect the integration rule for logs to also be fairly simple, and that's the case. Remember, back when we were doing derivatives of log functions that the derivative of natural log of x is 1 over x. This is why I think the integration formula is going to be simple as well. So, thinking backwards, shouldn't the integral of 1 over x dx be equal to the natural log of x plus a constant of integration? The answer is almost. There's one thing that we need to remember. The domain of the function f of x equal natural log of x is an open interval from 0 to infinity. You can't take the logarithm of a negative number. The formula actually works as long as we adjust the integral to say, the formula the integral of 1 over u du is the natural log of the absolute value of u plus c. Written that way, the formula is the way we want to use it and remember it. So we're going to begin from that base formula. We'll call it the log rule for integration. The integral of 1 over u du is the natural log of the absolute value of u plus a constant of integration. I do want to say one thing before I begin with examples. This is probably a really good time to remind you, back when we studied the general power rule for integration, whether you realized it or not, it never worked when n was equal to minus 1. The formula says if you integrate u to a power, you increase the power by 1 and then multiply by 1 over that. But notice that if you're multiplying by 1 over n plus 1, that means if you let n be negative 1, you would be dividing by 0. So that's why the formula that we call the general power rule for integration never worked for minus 1. We didn't make a big deal about it because we knew the gap would be filled in when we got to this. So I guess what I'm trying to say here is the log rule for integration is basically the one case where the general power rule didn't work, the case where n is equal to minus 1. It's the fill in the gap formula for the general power rule, as it turns out. Having said that, let's jump on to the problems and see how simple they actually are using our new rule. Remember, we're still doing direct substitution method here. Suppose we have the integral of 1 over the quantity 7x plus 1. We want to integrate that. We notice this time u should be the denominator. So that's what we do. We let u equal 7x plus 1. Calculate the differential. Du would be 7 dx, and then solve for dx, and you get dx equals 1/7 du, or you could write du over 7. Same difference. Now we can substitute. The denominator becomes the u, and the dx we just found out was 1/7 du. Plugging that in, and also noticing that a constant factor can always be moved outside the integral sign, we can write that as 1/7 times the integral of 1 over u du. That is exactly our log rule for integration formula, and we know the result will be the natural log of u plus the constant of integration. Don't forget the 1/7 out front, however. And we're still not done because we artificially put the u into the problem. When we get to the end, we've done our integration, we have to take the u back out and put in whatever u is equal to, in this case 7x plus 1. And we have our solution. 1/7 times the natural log of the absolute value of the quantity 7x plus 1 plus a constant of integration. Practice, practice, practice. Let's do another one. That one looks sort of awful, but if you think about it a minute, it's not really. The first thing I would notice is if it's going to fit our log rule for integration formula, the denominator has to be u. So that's what I'll choose. Let u be equal to x cubed plus 3x squared plus 12x. Calculate du. That would be 3x squared plus 6x plus 12 quantity dx. You need those parentheses. And then if you factor out that common factor of 3, which most of the time you need to do, we didn't exactly match what was left up there. we get 3 times the quantity x squared plus 2x plus 4 times dx. Now that's exactly what's in the numerator of the integrand, so that's a hopeful sign. We are off by a factor of 3, but the rest of it is what we have in the numerator. Go ahead and let's solve for dx. If we divide both sides by everything that's multiplied by dx, we get dx is equal 1 over the quantity 3 times the quadratic x squared plus 2x plus 4 times du, or you could write it as du over that, whichever you like. Now here's a part that you need to think about a little bit. The dx is that fraction that I just came up with. The u is the denominator. The x squared plus 2x plus 4 in the numerator is going to divide out with the x squared plus 2x plus 4 in the denominator, leaving only the 1 in the numerator and 3 and the u in the denominator. And that 1/3, being a constant factor, can be moved out, and you end up with the exact formula above that tells us that the integral of 1 over u du is the natural log of the absolute value of u plus c. Don't forget the 1/3 is still sitting there. And once we finish the integration, we have to get rid of the u and put back in the x's. In this case, u was x cubed plus 3x squared plus 12x, and we have our solution. Again, it looked messy to start with. There were a lot of things to write down, but the process is really the same in any case. Practice makes you better at this. How about this one? Well, this one could be a little tricky because you see that exponential in there and you say, well, doesn't that belong back with the exponential problems? But here's why it doesn't. If you think of the denominator as being the u, then the derivative, the du part, is going to involve the exponential. So when you take du, the derivative of 4 is 0, but the derivative of e to the x is e to the x. So the differential du is e to the x dx. So what's happening here is that this is actually a log rule for integration problem, and the differential captures that e to the x is sitting in the numerator. You might need to think about that a minute, but this is a formula where the u is the denominator, which means it's going to be a log rule for integration problem, and the e to the x in the numerator that might have fooled you in the beginning gets captured inside the differential for du. And let's see how that plays out. Of course, the next step is to solve for dx, so we end up with 1 over e to the x du, or du over e to the x if you'd rather. If we plug in the u in place of 4 plus e to the x and let dx be 1 over e to the x du, you see what happens. The e to the x's divide away. Like I said, the e to the x got captured by the differential du. Now it's being divided out, and all you're left with is the integral of 1 over u du, and now you can see why this was a log rule for integration formula. You might call the problem tricky, but I would say you just have to think about it and expose yourself to it, and then it starts to be second nature when you see a problem like this. Aha, I remember what happened last time I saw a problem like this. In any case, integral of 1 over u is the natural log of the absolute value of u plus the constant of integration. And the last step, as always, is putting the u out and the x value, which in this case is 4 plus e to the x, in. And you get the answer, which is the natural log of the absolute value of the quantity 4 plus e to the x plus a constant of integration. Again, practice makes perfect on these things. I want to end on a final point. In the beginning, I mentioned that some people like the matching method, some people like the direct substitution method, but we began with guess and check. I just want to say that guess and check is still in the game. If you're good at it and you see some simple problems that involve exponentials and logs, feel free to use guess and check. It's totally up to you, but it is still in the game here. You can use it. And I want to end by just showing you an example of where you could use guess and check fairly effectively. I'm going to choose the example, integrate e to the 2x dx. And again, I'm going to guess because I know the integral of e to the u is e to the u, so I'm going to make my initial guess that the integral of e to the 2x is e to the 2x. What does guess and check say to do? It says to check your guess by differentiating and seeing if you get the integrand. Well, let's see. Checking the guess, the derivative of my guess, the derivative of e to the 2x is e to the 2x times the derivative of the exponent, which is 2. So that's just 2 e to the 2x. So no, I didn't match it exactly. I'm off by, well, I'm twice as big as I needed to be. I wanted to get e to the 2x, but I got 2e to the 2x. So my guess was double what I expected, so maybe I'll adjust the guess and say, well, okay, if my guess was double what I wanted, why don't I adjust my guess to be half of my original guess? So I'll adjust my guess and guess that the result is 1/2 e to the 2x and check that. Now I've got to check my adjusted guess by taking the derivative of it. Well, the derivative of 1/2 e to the 2x is 1/2 times e to the 2x times the derivative of the exponent, which is 2. But 1/2 times 2 is just 1, and I end up with e to the 2x. Now, my adjusted guess matched the integrand exactly. That means the adjusted guess is correct. My adjusted guess was 1/2 e to the 2x, and because the derivative of it matched the integrand, it was correct. So by guess and check, I know that the integral of e to the 2x is 1/2 e to the 2x plus the constant of integration. Like I said, you never have to do the by guess and check, but if you feel like you're good at it, you can choose to do the simpler problems as guess and check problems. But it's totally up to you.